Okay, let's rule them. All right. Let's see. A few topics today. What I was going to do is I kind of introduced the switch capacitor stuff last time. I think I'll finish that up next lecture, actually, because I want to do the RF business today. And we'll hopefully have that problem set out to you by tomorrow. Okay, I'll work with TA this afternoon. And it'll be due next Wednesday. And like I say, basically, way to think about this RF problem set is we'll sort of add it into the queue to your group of homeworks, but we'll throw out now two homeworks. That's a really good deal, right? Okay. So throw out two homeworks, okay? So in other words, if you don't do this one, it just gets thrown out. If you do this one and you had one that I throw out one in any case, right? So if you had more than one that you didn't turn in, well, this one could take the place of that one, okay? And if you did a really good score in this one, it could be higher than maybe one of your other scores, and it could take place of that. So it can't hurt you, it can only help you. That's the idea of this, okay? And we'll have it due next Wednesday. Okay, any question about that? Right. Hopefully I'll get that out by tomorrow, okay? I'll do lecture day on it. You'll see that this material, this RF design stuff, isn't that different from what you know already, okay? But fortunately, there's not a lot in the book or anything like this. You're going to have to sort of think on your own on this one. Project. Okay, so I had some questions in office hours today about, what do we mean by the settling time thing? I kind of went over it a little bit last time, but let me do it again, okay, just to kind of help you get the understanding what the figure of merit basically is all about. Okay. The input, so here's our circuit. Now, something to notice right off the bat here is there's no resistor load, but the feedback network itself acts as a load, right? So don't ignore that fact when you're thinking about how the circuit has to work, right? Remember what we talked about, feedback loading acts as a load to your basic amplifier, so that's going to be important to you. So this essentially has very close to the same issues you had with your earlier amplifier, okay? Okay, so we put in a step. This is V in, and here's V out. And ideally, this is a factor. These resistors are ratioed. This is 2 times Rn, and this is Rn. So there's a factor of 2 here. And so the output will be twice as big. So this goes from minus 0.15 volts to plus 0.15, around 0. This should go, ideally, immediately to minus 0.3 volts, because it's inverting, right, to plus 0.3 volts, right? And then if you have the other transition, it'll go up again, do the same thing, right? So now, so that's the ideal response. And if we begin to look, let's sort of blow this area up here. This is the 0.3 volt response, and we have a specification for you, plus or minus 0.1%. So let me draw that in. So 0.3 volts plus 0.1% would be 3.003 volts, right? 3 millivolts, I guess, right? And this would be 2.997 volts. So this is the error bars, and we're saying your circuit is settled as long as it gets within this error bound around 0.3 volts. This is plus 0.1% and minus 0.1%. Okay. Now, there's several parts to the settling time problem. There's one part that's independent of time. Okay. It's a static settling time, static settling response. And the static settling is if, this response to this amplifier should be 1 over f times t over 1 plus t. Well, modulo the Rn and stuff is, but basically this thing should have a gain of exactly 2, because we'll assume these resistors are exactly 2, factor of 2 apart, okay, times this other term here. So we'd like this, if we have 0.15 volts in, we should like to have, you know, plus or minus 0.3 volts out. Okay, this is 0.2997, I guess, right? Not 3 volts. Right. 0.3 and minus 0.2997. So this is I'm looking at is right around this signal right up there. Well, what this is actually going to be, instead of being exactly 0.15 to 0.3, it's going to be 0.15 to 2 times A0F over 1 plus A0F. This is the DC gain. There's nothing to do with time now, right? So let's come back to the old stuff we did, okay? And I can write that as 2, so my input signal is 0.15 volts, right? Times 2 should be 0.3. Then I have this error. And if I rewrite that as 1 plus A0F, whoops, 1 over A0F, just divide top and bottom by A0F, this is approximately equal to 0.3 times 1 minus 1 over A0F, and, you know, so on, just the geometric series. So you can sort of see this term right here, this 1 over A0F, these are 1 over A0F squared terms and so on, so they're probably pretty small compared to this term. So in order to get inside this bound of 0.1, how big does A0F have to be as a minimum? What's the answer? 1,000, right? And if this is less than 1,000, you're never going. It's going to come up at, you know, just beyond the edge of this bound right off the bat, right? Okay, so it's got to be at least 1,000, and it probably should be a little bit more. Now, why should it be a little bit more? Now that's what I'm going to talk about now. We don't exactly have this. So that's the static settling, independent of time. So that gives you a spec on your gain. Now, the other part of this is not what the output response does when you put an input in like this. It goes into 2 modes. There's a first period, this linear ramp happens. And that's this slew rate thing we've been talking about, which is basically C sub C over IS over C sub C, right? All right, IS over C sub C. So this is what the slew rate's approximately equal. So more current, higher slew rate. You want to make this as fast as possible. This is in volts per microsecond, right? Volts per microsecond. So faster this IS, this is smaller C sub C, better off you are. Okay. Now, after the slewing, that's when the front pair of transistors are kind of in a nonlinear regime. They come out of the nonlinear regime. Then we go into the next mode, where this thing begins to settle out. And this is the small signal. So this is sort of the small signal settling time. Okay. The time that's of interest to us, so if I kind of blow up, here's the error bars right here. If I sort of blow that up in this region after you've gone through the slew rate, because you're clearly way out of the error bars during the slew rate period, you're beginning to get close to settling into this response, then what we're going to see is this thing does this. It's kind of, you know, wiggles around potentially. Now, the settling time is defined as once you enter this bar, the plus or minus 0.1% around your final answer, and stay in there, okay, then that's the settling time. So it's the last time you entered. So like here, let's say this is just below there. So this entered right at this point right here. So it's at this time, which is when we call the settling, the circuit has settled. So it's the time from t equals 0, when the input makes a change, right to the point where it finally gets inside the error bars, okay, which is, let's say, right about there. So this is t settle, kind of rise time. So this is the rise time of the output, right? There'll be another one on the fall time, because the circuits don't necessarily have to be perfectly symmetrical, especially in the nonlinear part response. Okay. So you look to see where it enters that error bar, and then once it's there, you call that settled out, and you measure the time from t equals 0 when you did your input to your input there. Now, clearly, if you've made it so that you made your gain as small as possible, so it finally is settling out to this 0.2997 value, you can sort of see what's going to happen. This thing's going to keep wiggling, and it's going to keep coming out of the region, the error region, that you allow called settling, right? Until way, way out here, right? I mean, maybe forever, right? So there's an advantage to having the settling time, the static settling, be the error from that, A0F, be fairly large. Error fairly small, right? You want this thing to be settling near the, have a fairly small error there. So then it can wiggle around a bit and still be inside the error bars, because it's going to wiggle around that small signal settling. I mean the static settling response. Okay. In other words, here's where the static settling voltage, whatever it is, 0.2998. Okay. It's going to be wiggling around that. Now, it doesn't necessarily have to do this. It can be doing this as well, right? Now, why don't you want to make this gain really huge? It has to do with this small signal settling. Now, let me explain that relationship between small signal settling. This is the time when it's after it's gone out of slew rate and it's doing this other stuff. If you remember back earlier in the year, a few weeks ago, when we did the bandwidth of a closed loop amplifier with feedback. Okay, remember I did this case? So I said, okay, let's make it just sort of generic here. This is A of omega. We feed it back, so it's this circuit right here. And let's say A of omega, and let's make this F, okay? Let's say A of omega is characterized by one pole. So this works for a one-pole response. It doesn't work for higher order ones, but the same kind of dependency that I'm going to show you right now holds even if you have a multi-pole response, okay? Multi-pole response with feedback is very complex, but it kind of adheres to some, tendencies that I'm going to show you right now. So let's call this the compensation pole. This A of omega has one pole in it, and we'll call that the compensation pole at omega C. So this is the frequency response of this op-amp, only one pole. Let's say F has no poles in it. Okay, so it's just frequency independent. So the loop gain of this thing is equal to A of omega times F. What I've calculated, if you look back in your notes, okay, if we look at the open loop response, or the loop response, right, T of omega, and we plot that, it's just equal to this, what's it going to look like? It's going to look like, here's omega compensation, okay, and, okay, so this is that's what it is. Okay, now, if we put this circuit into feedback, okay, what happens? First, the response becomes equal to, this is V in, this is V out. The closed loop response, V out over V in, is equal to 1 over F times T over 1 plus T. What do I want to do here? Okay, all right. So this is actually equal to what? This is A0F over 1 plus A0F times 1 over F. The F's cancel. So this was a gain of A0, and you see what this really is becomes equal to A0 over 1 plus T. So that 1 over F T over 1 plus T thing really means that the gain is dropped from being A0 to A0 over 1 plus T. But what I also showed, though, what happens in this feedback is that the pole of the closed loop amplifier, the pole of this, goes from omega c to 1 plus t times omega c. Remember that? So in other words, instead of the pole being here, it's moved out to 1 plus t times omega c. Well, this is a unity. This falls off 1 over omega. So if we go up in gain by 1, if we go up in frequency by a factor 1 plus t, this is inversely proportional to frequency. That means our gain drops by 1 plus t. And where does that end up? This point right here, this is what the closed loop response was. It was actually the gain is decreased by 1 plus t. So what it really means is it kind of comes back to this curve. So what happens is this is the closed loop response. And this is the loop response, okay? Loop frequency response, all right? This is t of omega. And this is 1 over f times t over 1 plus t. But notice what happened here. The frequency response of the closed loop amplifier is now sitting out here. Okay, it's increased quite a bit. What's all this about? Now let's get back to where we started from. What I'm talking now is about this small signal settling. So this is the response of the amplifier in the closed loop condition. That's what we're talking about here now. So the amplifier has a loop closed. We're looking at the time response of the closed loop response. This is the frequency response right here of the closed loop amplifier. So let's call this omega unity, okay? This is that point right here. Let's call this the unity gain frequency, okay? If we make f equal to 1. So this would be true if f is equal to 1, okay? Now, if we have, so here's the response that we're talking about. Let's take f equal to 1. This is omega unity, okay? This has a response of 1 plus, j omega over omega unity, okay? All right. If we do sort of go to Laplace domain, okay, right? This is like 1 over 1 plus s over sp, okay? Okay. The response of this thing will be equal to e to the minus t times sp, or roughly e to the minus t times omega unity. So the time response of a single pole amplifier is related to its 3 dB frequency, right? We do RC, right? If this is equal to RC, 1 over RC is our unity gain frequency. Let's think about it that way, right? Then the time response associated with an RC, a circuit like this, right, is e to the minus t over RC. Right? So what this says is, what you want to do is to keep this amplifier, the closed loop response of this amplifier, which is related to its compensation pole, okay, as high as possible. So this settling here is related to the bandwidth of the amplifier I'm trying to get to, okay? And since this is equal to compensation divided by A0F, you can see that this pole here, as it moves back to try to compensate for more gain, you're going to end up with having to if this whole curve moves up, right? We'll have to move this pole back. We're going to reduce the bandwidth of that amplifier. So here's the point. More gain helps out the static settling response, but it slows down the closed loop amplifier response. So your small signal settling time here will get slower. This ripple here, all the time constants associated with this will get less. It's not a direct relationship, because once you have multiple poles, which you're going to have in your amplifier, this single pole analysis I did won't quite hold. But it's kind of the right tendency. So settling, slew rate, you know what that's due to? It's due to the current and the compensation capacitor. But remember how it's related to, I did that little analysis and showed you how it relates to the stability problem. You're not quite free to just to go in and change ISS or reduce C sub C, because you have to worry about that. That's set by some of the stability criteria. So you got a little box there on you. This small signal settling time here, you're kind of stuck a little bit by the gain bandwidth product of your amplifier. As you make the gain bandwidth, as you increase the gain, the bandwidth's going to get less. That's what this closed loop bandwidth's all about. So what we're going to have to, that will slow this down. So you want to reduce the gain as much as you can in order to make the small signal settling okay. And the final thing is the static settling. You want to reduce the gain as much as, want to increase the gain as much as possible to get yourself in the middle of this error bars with the static settling. But of course that will slow down your amplifier, which will slow down your small signal settling time. That's your project. Okay. Any questions about that? So there's three things: slew rate, small signal settling, which is gets slower as you ask for more gain, and static settling, which gets better as you ask for more gain. So you see things are sort of fighting each other here a little bit. Right? But that's pretty classic, yeah.
What was static settling on the curve?
Static settling is where you finally finish out. It's where it finally ends up. Static is after all the time response stuff's happened, where you finally end up. And that's this A0, this term right here.
The value?
The value is, yeah. The static, it's not static, I'm sorry, did I say static settling time? The static settling value, I guess that's what I meant. Yeah, I'm sure. Static settling time doesn't mean anything. Okay, so pull that off. I shouldn't say that. Static settling value, where it finally settles to after a long period of time. If this is this outside this bar, if static settling value is outside the plus or minus 0.1%, the thing will never settle. You'll never meet the settling time. The settling time will be infinite. Got it? Can you draw that again?
What was the other one?
The other ones? Okay, let's try again. Okay, so we step the input like this, the output does this. So what happens? It hopefully, ideally does that. It ideally ends up exactly at 0.3 volts. But what it'll do is it'll first do the slewing period. After it gets within, when those input pair transistors get back into linear region operation, after one stops cutting off, you're within, that input pair is getting within a VD sat or so of its final value, right? And what's happened here is, if you look at this amplifier, we put a big step here. This output doesn't change very quickly. So what happens is there's a big step. It shows up across this input differential pair, and this output starts to change, right? It starts to change, feeding back a voltage here to drive this voltage back to zero, back to a very small value. But it takes a while for that to happen. Until that happens, until this error voltage across here gets less than a couple VD sats, this input differential pair is in nonlinear operation. So that's what's happening down here. We're in this nonlinear operation regime for a while. Then finally, when you get near the answer, this error voltage is being brought back down to something near zero. Then we go into a linear region settling. And that's what's happening here. So this is nonlinear period here. And here we're in a linear region. And finally, this thing will finish out, depending on its gain, to some value. And this gain, as I described, was going to be sort of 1 over f times 1 minus 1 over A0f. And so there's an error here associated here, and that's where where it finally gets to. Okay, so nonlinear settling, small signal linear settling, call this linear settling or small signal settling. Because our small signal analysis works now. Okay, it doesn't work out here. And then finally, it's the static value that we finally end up to. Static means it's the value it's going to be forever afterwards, after all this time response stuff is settled out. So that's the settling response of an amplifier. This stuff's really bad. It's this region right here. This is generating like harmonics and things like that. So this is really very nasty. I mean, you put in a sine wave, you don't get just a sine wave with a phase shift out. You get other sine waves out. I mean, this thing is the sine wave, instead of looking, like a sine wave, it has periods in here where it gets flat, and that's creating all sorts of harmonics. Right? So, okay. Do the 13th. Okay, I had another one. I was going to do it a while ago, but let me do it right now, sort of odds and ends. Super source follower. You guys love super source followers, right? I don't know how many people use super source followers. Okay, let's analyze a super source follower. I thought it's a really good circuit. I just since you guys have such familiar with it. Another review on feedback. Super source follower is a feedback network. Okay. Let me get it right here. All right. Okay. What kind of feedback is this? Circuit you've used a lot. Series shunt. Any other takers? Why is it series shunt?
For the
Why that mode today? Okay, all right. So we're feeding back a voltage. So where's the voltage coming back from? V out here, it looks like, right? So here's the feedback coming in. So what's the feedback factor here? 1. Okay? So he said this is the feedback. So here's V feedback voltage. Okay? Here's the error voltage being developed across this transistor right here. Okay? That's good. And so that's series feedback. And what are we sensing? We're sensing V out directly, feeding it right back to this input. So this is a shunt sensing. So this is exactly right. Series shunt. Okay? Let's figure out the loop gain of this guy. So what's the loop gain? Yes?
Why was the feedback? How do you know the feedback is over there? Because there's another thing attached to the output.
A little music interlude here. I just want sorry about that. New phone. I haven't quite got it under control yet. You know how these things are. Okay. Your question was, how do I... What was your question? How did I know it didn't go through? Well, take a shot at it. Well, where do you think it might go? Go down through here somehow, or? Well, what's the feedback from here to here? What's the transfer function in this direction? None, yeah. Take the none. You don't go backwards through a transition from drain to gate, right? So there's essentially no signal hardly at all doing that, right? So like the signal's going in this direction. So what's our basic amplifier look like? Our basic amplifier is going to look like this. Let's call this transistor 1, transistor 2. Okay, now, we've got to do something with these two nodes here. This is the feedback network. So what do we do looking into the feedback network? That's what we want to tire. So this is the loading effect of the feedback network in some sense, right? So what do we do on this side for a series shunt feedback network? What will we do at this point? How do we model the feedback network from the point of view of looking from the basic amplifier? What is it? Short. Okay, why is that? Well, you're looking in and you're seeing, so here's the feedback. It's a wire, right? And it's V out's the other side of this thing. So looking in from this side of here, we're looking into a voltage source, okay, which is going to look like a short circuit. So basically, it's like a short. So this guy we just short. What about this side? We're looking in this direction. So what do we see looking that way? Current source. Open. Exactly right. So this is open. So this guy just sits there. So now we need to figure out the gain from here. This is V out of the basic amplifier. Okay. Okay. So what is V out over V in? Okay. Who can tell me that? Let's forget that chi equal to 0. So what's the gain? What's the basic amplifier gain of the circuit? What is it? GM1 RO1 times GM2 RO2. Yeah, exactly right. So in other words, the gain from here to here, that's GM1 RO1 because we have an output resistance here of RO1. And gain from here to here, because we have this as open circuit up here, it's going to be GM2 times, excuse me, RO2. So here's the gain. So this is our AV of this circuit. Okay. T is equal to AV times 1 equals to AV. So this is T. So what's the output resistance of this basic amplifier? We need output resistance of the whole circuit, right? R out is going to be equal to R out of the basic amplifier, right, divided by 1 plus T for series shunt feedback. Okay? So what is R out? So looking into here, what do we see? RO2. Good old RO2 is all we see there. So R out of this basic amplifier is equal to R02. So we plug into here, we get R02 divided by GM1 R01, GM2 R02. The R02s cancel out. We end up with 1 over GM1 times GM2 times R01. So instead of the output, that's why it's a super source follower, right? Instead of just seeing output resistance of 1 over GM, you see it divided by this GM2R01, which is the gain of this feedback circuit we have here. Okay? Good old super source followers. That's why you saw this circuit had some interesting poles going on when you use this thing, right? Because there's a high gain stage right this point right here. Here's a high output impedance. There's a lot of gain to this point, okay? So you've got a point here which is a fairly high impedance node. That's, you guys started seeing peaking from this response, from using this circuit in your last project, right? Because right in here, look at this is R0. You're going to see this, it's not a lot of Miller multiplication because the gain's only 1, but you're still going to see R0 times this capacitance on this node right here. Right? Okay. Question about that?
I'm sorry. Why did you say there was peaking?
Because this is a amplifier and it's got a pole associated with it right in the center here, right?
Right, but why would that?
What?
Oh, that peak then.
Well, it's just we've got now there's a couple of poles in this circuit, right? I'm just saying there's this. As we know, what's the phase margin of this circuit? Okay, that's what we need to work through to figure out what the phase margin of this circuit is, right? It's got unity gain feedback, lots of feedback, right? It's got a pole sitting in here, and there's probably another pole sitting at this output, okay? So you got a couple of poles here to deal with, right? Depending on how much capacity in the output. So 2 poles, you have a feedback amplifier with quite a bit of gain, right? GMR node squared. So what's the phase margin of this circuit? And that's what will cause peaking. Right? Why do we have peaking? What causes peaking? Remember when we did this plots of the if you have a circuit like this, okay, this is frequency response of, this is V out over V in, okay. As we have less phase margin, what happens is this circuit will begin to do something like this, right? So the phase, as you get to phase margin of, I don't know, 30 degrees or something like that, you get significant peaking. So this is a feedback network. There's a phase margin associated with it. The phase margin gets less than, I don't know, 45 or 50. You begin to see some peaking in the frequency response. Try it.
I remember that, but then I always just was like, oh, okay, I accepted it. But then, can you explain why it peaks?
Why
with the
peaks?
phase?
Okay, so it's actually, okay, so that's good. When we do our T of omega test to figure out phase margin, right? Let's say here's the unity gain, here's our compensation pole, and we set this thing to have a certain frequency response, and here's our unity gain frequency, right? So we set mega compensation. For this case, let's say there's 2 poles, and this is a 45 degrees of phase margin case, okay? There's a lot of other poles going on here, right? And I showed you, what happens, when you put a circuited feedback that has multiple poles and zeros, the poles and zeros just move all over the place. Fortunately, for us, because we don't want to figure out that problem. That's a really tough problem to figure out. Spice can do it, but it's by us just looking at what's happening at this first pole where the unity gain frequency is, at that point right there. If we check this phase margin number, it fortunately tells us a lot about what happens, even though there's lots of other poles out here that are moving all over the place when we put it into feedback. This phase margin number that we can check with this loop response tells us a lot about where the poles are after we close the loop. Okay, that's a big step. There's no reason you might believe that's true. Because those poles are moving all over the place. But it is true, okay? And this first part here is, what we're talking about is the lowest frequency poles. What's going on up higher here? We just have no clue what's going on, okay? But it tells us a lot about what's happening at these lowest frequency poles. And there's a very good relationship between that phase margin number and this response. And what this really is, if we plot the poles, what's really going on here, if we only had 1 or 2 poles to deal with, right? Let's just say, take that case, and that's where this is really clean. These poles are getting, after we close the loop, they were on the real axis now. So this is the S-plane, right? This is J omega, this is sigma. What's really happening as we have less phase margin, if we look at the pole location, as the phase margin gets smaller, these poles are moving towards the axis. In fact, when you have 0 degrees phase margin, the poles are right on the axis, and that's an oscillator. If the poles move over into the right half plane, where you have negative phase margin, the thing's oscillating. Okay? So really what's happening as we have less phase margin, the poles are getting closer to the axis. They have more phase margin, they're moving away. If you plot the frequency response for a set of poles which have a real part, this is the real part of the pole, right? As the real part gets larger, you'll see as the response has no peaking to it. As the real part gets smaller and smaller, you'll see that these poles have a more and more peaking effect, right? What does our poles look like? Closed loop poles look like this. they're at 1 plus j omega over omega pole, and there's a real part plus a j omega imaginary part. That's this where this pole is, right? And it's times its complex conjugate, 1 minus j omega over omega real minus j omega. Oops, like this, right? The real imaginary part of the complex of these poles, okay? So these are the complex conjugate pair, okay? And as this sigma gets smaller and smaller, this thing gets to be more and more unstable, okay? So there's a bunch of things that are coupled here. Small phase margin. Now, so let's finish up our little story earlier today then. So this peaking here, what does that do? This is frequency response. This is frequency domain response. What's that do in time domain, which is what you're talking about in our small signal settling response, right? As this, okay, remember we talked about this is the closed loop amplifier response. This is what I was talking about when I, said a little bit earlier about having this closed loop amplifier have a higher and higher response. Well, that's this number right here. This is that plot right here. As you have less phase margin, you get this peaking here. I told you this related to the settling time, the small signal settling time. Well, this phase margin relates to the small signal settling as well. As you have smaller phase margin, this thing, instead of going up and staying flat, it gets up. As phase margin gets less, it wiggles more. It's more unstable. As it gets near instability, this thing just keeps wiggling on and on and on. As you have more phase margin, this thing gets less. So this is phase margin of 90 degrees. Okay, 90 degrees phase margin. Boy, there's no ringing at all. Right? As you have smaller and smaller phase margin, 0 degrees phase margin, it oscillates forever. I don't know, the critical damped thing is like 60 degrees or something like that, I think, or it gets up as fast as it can and doesn't ring. It doesn't hurt to ring a little bit. It doesn't hurt anything. So playing with phase margin, you will be able to adjust, in some sense, how much ringing you have here, and that'll help a lot on your settling time response, right? Settling response. If you get too much phase margin, thing's stable, but then it just rises really slowly. Right? What? Well, this is almost independent slew rate. I shouldn't draw that. The slew rate will, so this thing will go up. Yeah, I shouldn't. Slew rate will be the same. It's after we get out of slewing I'm talking about here. This is the response. So that's a good point. The slewing stuff will be the same if we don't fool around with C sub C and ISS, right? This just comes from ISS over C sub C. Okay, that's how much current driving the capacitance, the large capacitance. It's after that period, it's this last part here that's going to get really slow. It's this. Okay? So slew is kind of one thing, small signal settling is another thing. This is all small signal settling I'm talking about here. Okay? Take a couple minute break and we'll do some RF stuff. Yes, Josh. What?
One was, back here.
Mm-hmm.
You said transistors were in linear mode.
So it was cut off. The one was cut off. They're nonlinear.
I understand this stuff. I just don't see the connection with the transistor circuit itself. That would help a lot. Make a big step.
Okay?
You're applying at both ends, right?
Yeah, differential, right? Well, if I even put it one side, there's a common mode response. This thing moves around, so it's always be alternative.
Well, I mean, okay.
Yeah, okay. So this side goes way up, and this side goes down.
This turns on.
This guy turns off. That's what I'm talking about. That guy turning off puts the circuit into a non-linear mode. Okay. And this output here, it's driving a capacitance, right? So it just ramps. That's what I'm talking about.
then what happens?
Finally, there's feedback comes around.
Feedback.
Right, the circuit's in feedback, right?
So we have to have feedback in our circuit.
Absolutely.
Oh. We can't do it without the feedback.
You got to have the feedback. The circuit won't,
Huh? Circuit
What-
won't what?
it won't work, right? If you don't have feedback, if I do this, right, minus plus, I put a big step on here, no feedback, this thing will just stay saturated, right? I mean, this right? There's nothing.
So it'll just keep going like this forever.
Yeah, until it saturates.
Isn't that an infinite?
Well, then until some transistor saturates, right? I mean,
No.
then it'll just flatten out. No gain at all.
No gain?
No gain.
I don't see how that's no gain. It's even higher voltage.
Yeah, but if I put a little signal on here,
Mm-hmm.
this is just flattened out at VDD or something.
Oh, and so like this starts getting into linear region. Is that what
Yeah, so this thing's feeding back around. So this voltage is the feedback's coming into this node. Okay, let's say, right? This voltage is sitting way up here. Well, this voltage will come back here, and this voltage will rise and start to become equal to this voltage on this side. And when that finally happens, the differential voltage is dropping to a very small value again, and back into linear region operation.
Then why is it ring like up and down and up and down?
Because there's poles associated in this. There's a pole here and maybe another pole somewhere else, and with this feedback coming around, it moves those poles off the axis, like I talked about, right?
Oh,
And that causes the ringing.
okay. Phase margin. When you're talking about phase margin, how exactly does phase margin affect the circuit? Like I know you're saying like more phase margin goes like that, then less phase margin. I kind of don't.
Phase margin is related to when we close the loop. The pole location after we close the loop affects how close those poles are.
I know. But how does it move it this way with more phase margin? Like you said, it moves it this way with less, and it moves it this way with more. How does it move it with more? What's the equation?
Well, it's this sigma real part of the pole gets larger.
Yeah.
Okay.
Phase
I guess.
margin directly related to the real part of the pole.
Yeah.
What's the equation?
It's not that straightforward. I mean, it's inside. You might be able to work it out if you want to. For a single pole, or maybe take 2 poles, figure it out, and you may get some expression. But it's
So the value of this equals, right?
yeah, right. Yeah.
What's the benefit of a super source for?
What's the benefit?
Yeah, now we're going to use it.
Well, people used it a lot to drive the output resistance because they really got a really low output resistance.
Just for low output resistance.
Yeah. It's good for driving resistors. Yeah, a bunch of people use it in their projects. Okay. Let's let's give you the basics of what's different with RF design. So what we've been talking about up to now has been what we call baseband design. Okay, baseband, relatively low frequency. What baseband is changes over time. Okay, but why we differentiate between baseband and RF? RF, when you put something into an antenna, okay, in order for it to transmit any given distance, right? There's an antenna issue size here, right? I mean, AM radio is around 400 kilohertz, okay, but the antennas of AM radios, are huge, right? Your TVs are something around well, they can't mean huge if you really wanted to have a really good antenna. You could, people put antennas across, the length of their house, right? If you really want to get best response, right? You can always use a shorter antenna, just lose signal. The best antennas are about, a half a wavelength long, okay? The televisions, the size of the TV aerials, what they are, and they run around oh, it's like a couple hundred megahertz, that kind of number. Okay, a couple hundred megahertz. The UHF antennas, which are the smaller ones, that's around 400 to 800 megahertz. Okay, so we call these kind of frequencies RF frequencies, right? Okay, then cell phones run around 900 megahertz. A bunch of them are at. Then there's a bunch of phones up at 1.7, I think, gigahertz and 1.9 gigahertz. Okay. And then you might guess the antenna is getting smaller and smaller all the time. And in Wi-Fi, stuff 802.11b, that runs at 2.4 gigahertz. And then actually there's 802.11a, and that runs around 5 to 6 gigahertz. So over time, a bunch of years ago, is all you had AM radio. As technology has gotten better and better, we've moved up to higher and higher frequencies. And so now, basically the design that we're doing in our research project we have at BWRC, we're working on 60 gigahertz. You can talk to Sorab about that, and that he's designing circuits to work up at 60 gigahertz. Standard good old CMOS, okay. So the question is, how do you get circuits to actually work at all these different frequencies, okay, or how do you do this? So first thing you do, signal gets transmitted from, let's look at the receive side right now. The first thing the receiver does, usually goes through a filter, because you're receiving everything in the world. When you stick this little antenna up, okay, it's kind of tuned for one frequency, but all this other junk that's being transmitted in the world, you don't want to receive that. So you put a filter right off the bat, and it's usually a passive filter of some sort. It just kind of gets rid of other frequencies besides the ones you want. So let's talk about a Wi-Fi system. So let's make it 2.4 gigahertz. So it's centered around 2.4 gigahertz. This signal coming here at this point in time is really small. We're talking it's down on the microvolt level, okay? Maybe microvolts to maybe hundreds of microvolts kind of number. Okay, so this is really small. What we're trying to get to is to an A to D converter. There's a A to D converter over here, and it needs basically about, and let's say it's running at, I don't know, for 802.11, it's probably running like 40 megasamples per second, 40 megahertz. Okay, this is the sampling rate of this A to D converter I talked about last lecture, right? And then it goes into the digital processing afterwards. Okay, so it's 40 megahertz, and it needs a signal in input here, probably like a tenth of a volt, up to a half a volt, something like that. Okay, so we got something that's a microvolt, and it needs up to get to 100 millivolts. Okay, so we need a gain of like what? 100,000. If it was 1 microvolt to get up to 100 millivolts, 1 microvolt to a millivolt would be a gain of 1,000. To get up to 100 millivolts would be 100,000. So you need a gain of 100,000. Okay. For the really small signals, larger signals may only have a gain of 1,000. So you need a lot of gain. Okay. And remember, the stuff's sitting up at 2.4 gigahertz. The width of the band of interest is like about 20 megahertz or so. Okay. That's why we somehow got to get, but it's 20 megahertz around 2.4 gigahertz. So the first stage of a radio, what you do is you got to get the signal bigger. So you go into an amplifier, a low noise amplifier. The problem is every transistor creates noise. Okay? You don't want the noise created by your circuit to be bigger than the noise of your signal. Okay? So this low noise amplifier design is basically trying to make an amplifier that does a lot of gain, okay, with adding in the least amount possible noise. Okay. The noise, just to tell you how that works, is it's a little, the way you can model it is a little noise source in front of every gate. It just adds into the signal. Okay. So if you just think about every transistor, and the noise value is like 4 kT roughly times 1 over GM square root of that. So this is kind of the noise voltage. KT is the temperature, thermal voltage. 1 over GM. So as you make GM larger, the noise goes down. So you can see a problem here with power. If you want really low noise, you can do it by making GM really big, but then the power gets higher. Or you make the transistors really big, but then you got a problem with speed, right? Make a really big transistor, that's hard to, a lot of capacitance, so that's hard to drive. So that's all part of the LNA, and I'm going to talk a little bit more about that in a few seconds, okay? But you can't do it in one stage, obviously. The first stage is the most critical one, as soon as you amplify the signal up, any more noise that's added, this is really important for any kind of design generally. As you add noise here, you amplify the noise plus the signal. Then when you add noise here, the signal's bigger. So if the noise you add at this point is about the same as the noise you add here, the signal's bigger here, so the noise is less important. So it's really the first stage that's really important for noise. And after that, if you get enough gain in that first stage, then subsequent stages aren't a problem because the signal's been amplified and the little noise you added is the same amount, so it doesn't make much effect. So you've got to have some more gain stages. And you actually usually alternate gain with some more filtering. Okay? So here's our antenna. Let me start again here. A filter, LNA, more gain, and often you have to make this variable gain too, because sometimes the signals will be 100 microvolts, maybe it's a millivolt sometimes. Sometimes it'll be a microvolt. So the signal itself may change over a factor of 1,000, and that's the big problem with RF radio design. Because think about it, if you're sitting underneath the cell phone tower, that cell phone tower is putting out, 100 watts. Okay, and your little cell phone sitting right below it there is getting just creamed with all sorts of power, right? Okay. Then you get to the edge of the cell. So that when you're right next to the cell phone, you might be getting 10 millivolts into your cell phone. Okay, you get to the edge of the cell, it might be 1 microvolt. Okay, so you got to have somehow, if you have a gain of 100,000, which just makes the 1 microvolt just fine. When you have the 10 millivolt case, that's going to be 0.01 times 10 to the 5th, 10 to the cube volts. 1,000 volts. Well, obviously, what happens before that? Some transistor goes out of saturation, right? Went out of saturation a long time ago, right? So you got to have a lot of variable gain in order to get this stuff. So we have filtering, low noise amplifier, LNA we typically call it, then variable gain. Now this is all sitting up at 2.4 gigahertz. So all these amplifiers we have, remember what this looks like now. This is frequency versus amplitude of the signal, and this thing's sitting up around 2.4 gigahertz. There's a signal we're trying to amplify. So we can filter things here, get rid of all this other junk that's all over the place, right? And just try to amplify this stuff around 2.4 gigahertz. But this is pretty power-consuming stuff, as you might imagine, to amplify up at these frequencies, and to get a gain, this much gain. Think about what your project was like. Your circuit, you guys got up to 5 to 6 gigahertz and a gain of 1,000, right? Okay, well, that's kind of getting what you sort of have to do here, okay, right? Can't use feedback, obviously. These circuits are all open loop, okay, like your second project was. You don't want to amplify any much more at 2.4 gigahertz than you possibly can. So what you do then is you mix. You have a mixer. What a mixer is, it's just a multiplier. And the other circuit you got to have is a synthesizer. So this is the synthesizer, and this is the mixer. And these are amplifiers. So these are kind of the basic elements of a radio. What this synthesizer does, or this mixer does, is, let's say, what you can do, and you call this a direct conversion receiver. What you do is, you make the synthesizer at 2.4 gigahertz, the same as the carrier of your signal. 2.4 gigahertz in your synthesis. This is a sine wave at 2.4 gigahertz you got to create. This is a tricky little circuit design problem. Let me tell you, it's an interesting one. You use a bunch of strategies. It's a feedback circuit with a phase lock loop locked to a crystal, generally. You multiply this 2.4 gigahertz times your signal, and what do you get out? If you multiply two sine waves together, let's just do two sine. Let's say the sine wave, this thing will come in here. It's primarily a sine wave with some sort of modulation on it, amplitude or phase modulation or frequency modulation. But if you multiply a 2.4 gigahertz signal times another 2.4 gigahertz signal, what do you get out? Two signals, two frequencies. What two frequencies? What? Zero. You get the sum and difference frequencies out, right? If you take cosine omega carrier times t times cosine omega synthesizer times t, okay? What's the signal you get out of that? You get, I'm not exactly sure, but it's sine of omega c plus omega st plus, this is approximately, right? Sine of omega c minus omega st, okay? So you get the sum and difference of the frequencies. So here you're going to get something down around 0. That's the baseband signal, okay? And you get something else around 4.8 gigahertz. Well, you put another filter here, and you knock out the 4.8 gigahertz one, and you end up with the 0 gigahertz, the one that's around baseband. But remember, our signal will start off as being 20 megahertz wide. Okay, so it's, if we look at it, it's 2.4 gigahertz, and it's plus, 2.4 gigahertz plus 10 megahertz, and 2.4 gigahertz minus 10 megahertz. So after this mixer, it mixes it down to baseband, but all this other stuff, so you end up with a signal that looks like this. Here's 0 frequency, and it's kind of on both sides of baseband at plus 10 megahertz and minus 10 megahertz. Then you have an A to D converter. Let's say you have 4 times oversampling, so it's 40 megahertz A to D converter. Then you A to D convert this 10 megahertz signal. Okay. It's a little more complicated than that. Actually, we have 2 mixers, and we mix down with a sine and a cosine, 90 degrees out of phase. That gets rid of some phase dependencies. But basically what you do is antenna, filter, amplify, mix, filter, and then go to A to D. That's a direct conversion receiver. Sometimes what you do is you mix down to an intermediate frequency. People call it IF. Instead of going all the way to 0, you may go down to, I don't know, 100 megahertz. Okay? And then you do some more amplification, 100 megahertz, and then mix down again to 0. And this has to do with, there's some other mixing products that are going on here that I'm not showing you, and you have to worry about these other mixing products, and there's direct conversion has a problem with DC offsets and a bunch of very mundane things. But basically it's just amplifiers, mixers, a synthesizer, and then you get the AD converter. So that's what a radio is really all about, okay? And you do a lot of digital processing afterwards. Okay, so let's look at part of, now in this class, obviously we're not going to do it because we don't have any time left, but this is what 142 does. They worry about mixers, talk about synthesizers, these are oscillators and things like that. So that's kind of 142 material, okay? These are nonlinear circuits. You multiply 2 signals together, that's nonlinear, right? So that's 142. We've been talking about linear circuits. So L and A is really one of the linear circuits, or these amplifiers. So how do you do that? Up at these frequencies, we've got a new device, okay? Wow. And what a win. It's an inductor, okay? We actually begin to use inductors. And it wasn't until an inductor of any reasonable value at 400 kilohertz you couldn't put on a chip. I mean, these things would be huge, okay? It's when we started getting up in these gigahertz signals that the inductor sizes we needed were like on the order of 1 to 10 nanohenries. Okay, that's 10 to the minus 9th henries. Okay, that's like farads, right? Once you got in this nanohenry regime, you could put them on a chip. And what do they look like on a chip? What you do is take your metal level and you sit there and make a spiral. This is one of the classic ways to do it. And then you go down to some lower level metal and bring it out. And this spiral that you can put on the chip, and it's on the order, I mean, it's big. It's kind of like resistors are, right? I mean, resistors take a lot of area. They're pretty useful, but they take a lot of area. Well, inductors take a lot of area. In fact, if you look at a cell phone chip, you'll see these little spirals all over the place, okay? And they will dominate the area, right? In fact, when you buy a cell phone chip, you're mainly buying inductors, right? Little transistors, they're sitting down here, a little bunch of little transistors down here, but mainly you got most of these inductors. It's kind of a problem, actually. As we go to more fancy technology, the inductor stays the same size. We shrink our transistors down. They get smaller and smaller and smaller, but the inductor just sits there big and happy, right? And costing more and more, effectively, right? Because it's a per unit area cost for these things, right? So it's getting to be a challenge of how to design radios where you don't use inductors. Just like you didn't want to use resistors, how that was expensive to use resistors. Well, inductors, if you could try not to use inductors is really kind of a good thing to do. But now I'm going to show you why you really want to use them. Okay, right? So let's do an amplifier. Okay, you're on the job. Boss comes to you. Okay, you took 140. I know they teach you how to design amplifiers. What amplifier would you use if you had to design an amplifier at 2.4 gigahertz? Tell me. Need takers? This is the design problem. It's a transistor. It's a transistor amplifier. I'll tell you that. Okay, now what more? What configuration would you want to use? Need lots of gain. Don't think too hard here. What? A diff amp? Typically, we only have a single-ended signal coming off of the... you actually can make a differential, and sometimes, in fact, more often we begin to do that. You go through what's called a balun. And a balun basically takes a single-ended signal in and gives a differential signal out. But that's extra circuitry and stuff like that. So let's just say single-ended right now. Okay, so what would you use? Come on. Would you use a source follower? Common source. Great, exactly. All right. I knew some of you other knew this too, right? Okay, so good old common source. And an antenna can be modeled as basically a voltage source in series with 50 ohms. Okay? We can design circuits to be different impedance levels. And so let's say we could design our antenna to be 50 ohms. Okay? So basically our input looks like this. So let me just redraw this here. So here's our antenna voltage, okay? And it goes through a 50 ohm resistor. That's modeling this antenna. And it comes into our common source. Now what do we want to do next? We're trying to get a really fast circuit. So how might you want to, what would I put up here? Current source? What would be the next? Give me the rest of this circuit here. The load. What kind of load would I use? If I'm trying to go really fast. What? A resistor? What about Miller multiplication effects? Don't we have a problem here? If we go right to a load right here, don't we see a CGD here that gets Miller multiplied by this gain? So what do I do? Cascode it, right? I should cascode this thing, right? So let's cascode it. Go out to some V bias. So that gets rid of this Miller multiplication effect. Okay, now let's do a load up here. Okay, so now what could we put? We could put a resistor here. But remember, I've got a new element now. I've got an inductor. And here's where inductors are just super. Okay? What you really want to use as a load is an inductor. Now think about this. What's the DC voltage here at this point? If this is VDD, you have an inductor. What's the DC voltage on the other side of the inductor? VDD. The impedance of an inductor is J omega L. Omega equals 0. There's no drop. So using inductors, you are able to take the supply and stick it right on the drain. No loss. Wow, that's pretty neat. In terms of swing, what a really great deal, okay? Here's the other reason inductors are just great. We've got a capacitance hanging out here, right, from all sorts of stuff, right? Okay, capacitance to the next stage, and so on. C load. So I got a capacitor and an inductor together here, and in parallel. So let's look at the design of that. So this is grounded. And let's look up into the impedance of this. What is the in of this circuit? Okay? Well, let's put in here, so this is j omega L, and this is 1 over j omega C. These are in parallel combination. So Z in is equal to 1 over j omega C times j omega L over j omega L plus 1 over j omega C. I have no resistors up here at all. Let's multiply top and bottom by j omega C. That gets rid of this in the bottom, so I get j omega L over 1 minus omega squared LC. All right? J omega C times this, j's can't square minus 1, omega squared LC. So this is our impedance. Look at this. Isn't something interesting happening around omega equal to 1 over root LC? What happens to our impedance? It goes to infinity. So inductors can actually tune out capacitors. That's what we call it. This effect here. You put an inductor in, you design it in a like a tank. It's a tank circuit. Called a tank circuit. You take that inductor and you make it relate to the inductor like this. So let's make this at 2.4 gigahertz. So at 2.4 gigahertz, right in the center of the band we're interested in, we can get rid of effectively all this capacitance that's hanging off that node. Think about the pain you went through to deal with that capacitance. If you had an inductor, you can go in there and tune out the capacitance. Okay? You don't get inductors in your projects. Inductors have some really interesting issues, you might guess, adding poles and stuff like this, right? Okay, so this is all open loop stuff we're talking about here right now, right? So that's kind of nice. Okay. Now, and unfortunately, it's not quite that good. An inductor also has a little parallel series resistor associated with it, right? So it doesn't really go to infinity up here, but we call this the Q of the inductor, right? And the Q of the inductor is basically sort of omega L over R, okay? So as R gets small relative to omega L, this Q value gets larger. What do you get in a standard process? This is coming from the resistance of the wires and so on. Qs are typically down at 2 to 5 gigahertz, or sort of on the order of 5, maybe up to 10, something like that, right? Here's something that's really interesting. What happens up at 60 gigahertz? You look at this Q value. If R doesn't really change, omega goes up by a factor of 10, your Q goes up. So actually, at these really high frequencies, these transistors are getting even better. Why would you want to do something at 60 gigahertz? I'll tell you why I would do something at 60 gigahertz. 60 gigahertz has a huge amount of bandwidth available. There's 7 gigahertz of unlicensed bandwidth at 60 gigahertz you could do radios in, if you could do that cheaply. Right now, to buy a radio that works at 60 gigahertz would cost you like $10,000. Right? Because they use indium phosphide. They use these exotic materials. Right now, as we speak, all of a sudden, CMOS at 130 and 90 nanometer became able to do what people forever had to spend thousands and thousands of dollars to do. Pretty interesting. I mean, here's a big opportunity. That's why it's a research project for us. Radars on cars. They're going to put, future cars are going to have radars on them right there. There's going to be radars for cruise control. They'll put a radar in front. And what it'll do is it'll sense the car in front of you. And so you put this thing on cruise control. As you get close to a car in front, it'll automatically slow you down so you don't have to, do it yourself and, drop it out of cruise control. It's already happening right now on your little Mercedes that you may have or your high-end BMW, right? Because there it only costs, these little babies cost, $2,000 or $3,000 for these little radars. And if you're already spending $50,000 for the car, $2,000 or $3,000 more, who cares, right? So probably a lot of us don't have those cars, right? But think about if we could do that all in CMOS. If we can do that in CMOS, we'll go from thousands of dollars down to $20. And it'll be on all cars. What a huge product. That frequencies for radars are like 77 gigahertz. Just right at the threshold where CMOS can begin to do this stuff. They're talking about putting radars on the side of cars, your blind spot, for parking. They're actually doing some little motion sensors right now for parking. airbag deployment, just as you get ready to slam into somebody, in your accident that you're going to have, right? There's a little radar. It's going to get there, and it's going to figure out that you're going to, have an accident in the next 5 milliseconds from now because you're, coming in so fast. Right now, it happens, when you have an accident. The acceleration deploys the airbags, right? So you're all of a sudden, the car's stopping, and you're going forward at 60 miles an hour, right? Airbags coming towards you at 60 miles an hour. You two meet just, right behind the steering wheel there with a 120 mile an hour bang into that airbag, and there's a lot of injuries, actually. So what they want to do is actually figure out that the airbag is deploying, or you're going to have an accident, and then deploy an airbag first before you begin to sort of, you're sitting back in your seat and sort of launches it, fixes you in the back of the seat. Let me tell you, this is a huge volume product. I mean, if you guys want to start a company and figure out how to do something, getting in the automotive world is a tough thing. But once you have a safety thing like that, there's, how many cars are made a year? I don't know, 100 million or something like that, or 50 million or something like that. Every one of those cars is going to have that, like you have to have airbags now. They're going to have these kind of things. This is another huge product. I mean, this is kind of what you do in this world, in this IC world. You look around for new products like that have tremendous volume, because you got to have tremendous volume, because what we're doing in ICs is high volume manufacturing. It's going to be really cheap. But you find things like that, and boy, then you make $1 million off it, right? Cell phones right now are one of the biggest runners of all. This little thing I'm talking about right here, the money that's being made off cell phones, it's bigger than anything else right now. I don't know how many there's some number like, I think it's like 500 million cell phones are going to be probably sold next year. I mean, China itself is sucking in, a couple 100 million all by itself, right? I mean, it's cell phone selling there. You look for products like that, and boy, and you design things into that, and if you can beat other people's design, and you know how to do good design now, like your projects, except instead of being your partner or being your other people in this class, it's going to be people working down at Broadcom or Marvell or something else, and you're going to have to figure out how good can those guys do a design. Well, you don't quite know how good they are, right? And so you keep trying to figure out how to optimize, just like you did in this project. But if you can win, boy, I mean, tell you, there's just huge money in this stuff. And this RF area is just a really open area now, because CMOS is just on the threshold beginning to do that. I mean, cell phones 10 years ago, you couldn't do it in CMOS. Couldn't even think about it. Five years ago, it began to be dominated by CMOS, and right now, it's most all of them are CMOS right now. Okay, so we're going to get a little project using inductors, right? So I'll little project, little homework.